So in the chapter linear regression and optimization, right? In this chapter, which was a few chapters earlier from now, right? We discussed about gradient descent, why gradient descent is useful in finding minima and maxima. We discussed about stochastic gradient descent. We also looked at batch or mini batch or mini batch based SGD. We also understood why gradient descent, stochastic gradient descent, or mini batch SGD are useful in finding minima and maxima of functions, right? So in this section, we will look at, so this whole thing is basically algorithms. So SGD or gradient descent or mini batch SGD are trying to solve this problem. You want to minimize a function L of, let's say, weights, right? You have a loss function of weights and you want to minimize it with respect. You want to find the best W. You want to find the best W that minimizes this loss function. This is your target, right? So whenever you want to find or solve such optimization problems, these are called optimization problems, right? So SGD or variations of SGD have worked very well for us. But in the case of deep learning, the simple SGD, your simple SGD or even batch SGD or mini batch SGD cannot solve all the problems very well. We'll see why, what problems it has and things like that. But before we understand other variations of SGD or advances or more recent advances, and remember, most of these advances have happened in the last 10 years, right? These are advances on SGD, primarily for deep learning. We'll learn a bunch of these algorithms and how they work. But before we go and understand these algorithms, I want you to give a graphical understanding of what optimizers do or what optimization is all about, with a nice analogy or a comparison to descending a hill, right? Suppose you're sitting on a hill. Okay, let me draw some diagrams to explain this for you, right? What is our task? Our task is to minimize a function L. This is a function of weights and our parameters are weights, right? Just like in deep learning, just like in multi-layer perceptron or even in logistic regression, we're trying to find the weights, right? That's a problem that we're trying to effectively solve. Imagine, so let's take some examples, right? If this function L is as follows, right? Let's assume W is a scalar, just for simplicity. So case 1, case A, W is a scalar, means it's just one value, right? This is your W. Then I can plot L of W on the y-axis. If W is just scalar or it has one dimension, what does scalar mean? Scalar basically means it's just a one-dimensional vector. If it's just one variable, they can plot my loss, right, on y-axis. Now there are many ways this loss can look like. One way the loss can look like is the loss can look like this, right? We saw square loss, which looks like this, if you recall, right? Which looks like, this is like a parabola. Okay, this is like a parabola. Okay, that we studied probably in 11th class or something. Okay, so here in this plot, so let me draw it more carefully, just to get it more elegantly. Let's just say this. Okay, so this is the function. This is my L of W. This is my L of W. L. This is my loss function. This is the function, and it is a function of W. Right. Now here you have one minima here. So this is the minimum value, and it occurs at 0. Right. This is called the minima. Right. This function has no maxima. We talked about maxima and minima in a lot of detail in linear regression and optimization chapter, where we define what is minima, what is maxima, and stuff like that, right? This function has no maxima because as this increases, it will keep increasing, and this will keep increasing. So the maxima is infinity, but the minima happens at W equals to 0, right? So it has a minima, and it has only one minima. Right? Now let's take another example, right? Let's take a slightly different example. Imagine my W looked like this. Imagine my W is here, right? And if my L of W looked like this, let's say it looked like this. Okay, let me change it slightly. Okay, let's assume it looked like this. Okay, let's assume this is your L of W. Okay, and it goes like this. Let's just say. Now here, this is also a minima. This is a minima because all the points that are surrounding to this, right? This is a minima. W is a minima. Like this is W1. Corresponding to W1, you have a minima. We're calling it a minima because if you compare it with points which are close to this, minima, this is the smallest value. This point is also a minima corresponding to W2. Corresponding to W2, it's also a minima. Corresponding to W3 is also a minima. Right? You have three minimas here. But amongst these three minimas, this is the lowest amongst all the three. So this is called as global minima. This is called global minima because it has the lowest value as compared to all minima, and these minima are called local minima. These minima are called as local minima because this value is minimum compared to this locality, but this value is minimum compared to all other values in the whole function. That's why it's called global minima, and this is called local minima. Okay, number one. Number two, at minima, you always have your gradient or slope equals to 0. We saw this in the optimization chapter, right? At both minima and maxima, you have your gradient or derivative of the loss function with respect to W equals to 0. Right? Like for example, this is a maxima. This is a local maxima. These two are local maximas. Right? So here the gradient, the slope, the tangent here looks like this. Since the tangent is parallel to x-axis or your w-axis, its slope equals to 0. How does the tangent here look like? The tangent looks like this. The tangent here looks like this. The tangent here looks like this. Right? So to understand if your slope is equals to 0 or not, you basically draw a tangent and look at its slope. And that's what we learned in the linear regression and optimization chapter, right? So here, as we have seen, at both local maxima, suppose the function looks like this. Suppose this is your W and this is your loss of W, let's just say. Like this is your local maxima because the maxima can occur at many places. At maxima, your slope or your tangent, if you draw the tangent to this curve, right? The tangent is here and its slope equals to 0. What about the tangent here? The tangent here is also parallel to your w-axis or x-axis here, right? And hence, this is your local minima. But there is a special point called saddle point, okay? So at minima and maxima, right, your slope of your loss function with respect to W equals to 0. There is another type of point called saddle point, which looks like this. I'll show you how it looks like in more detail. At your saddle point also, you have, so let me just zoom in here, okay? How does it look? It looks like this. It looks like this. If you zoom into this region, this is how it looks. So if you take this point, of course, this is your W. If you take this point, and if you plot the tangent at this point, it looks like this. So even at saddle point, also your derivative with respect to your x-axis, your derivative of loss with respect to W is also equals to 0. So the derivative equals to 0 could imply that you're at a minima, maxima, or at a saddle point. All three are possible, right? Very interesting, right? So, and if you recall our stochastic gradient descent and stuff like that, we always said that we'll keep updating, right? What is our update function? W new equals to W old minus eta times derivative of loss with respect to W, right? We'll keep updating this. We keep running this in a loop where we keep updating the old value to new value, right? And we stop updating when this derivative becomes 0. And the derivative could become 0 at minima, at maxima, or even at saddle point. So sometimes your stochastic gradient descent, your simple stochastic gradient descent or mini batch stochastic gradient descent could get stuck at a saddle point. Because what happens at a saddle point? At saddle point, this derivative becomes 0, which means your W old becomes W new, which means there is no change. And when it doesn't change, you say, yes, I have converged. But instead of converging to a local minima or local maxima, you could have converged to a saddle point. Then what do? There are ways to get rid of it. So simple SGD or mini batch SGD could get, it doesn't always get stuck, but it could get stuck at saddle point if you just employ mini batch SGD. And hence, we will use some advanced techniques to avoid this problem of getting stuck at saddle points, number one. Okay, but I'm just defining a bunch of things for you, right? So there is another very interesting definition called convex functions and non-convex functions. And non-convex functions. We discussed this slightly when we discussed about optimization in the linear regression and optimization chapter, but let me just redefine it for you. Suppose if I have a function like this, this is my x or this is my w. Let's keep the same notation. This is my w, this is my L of w. Okay. Suppose if this is how my plot looks like. If you take any 2 points on this, okay, so you can break it into 2 regions, right? This region and this other region. So this other region, which is outside this. Now this is called a convex function. If you take any 2 points here and if you connect them through the shortest line, if all of these points which are there on the line lie in one region, if they lie in one region, it is called a convex function. Let me draw a non-convex function so that you understand it better, right? Suppose I have my w here, I have my LW here, right? Suppose if I have a function like this, okay? So I can also break this into 2 regions. This whole thing is one region, right? This whole thing is one region, and this whole region is the other region, right? Now let's take any 2 points within one region. Okay, let's take these 2 points. If I take this point and let's say this point, okay, let me just simplify it. If I take this point and this point, these 2 points lie in the orange region, right? They both lie in the orange region, right? But when I connect the line, if I draw a line connecting the shortest line connecting both of them, some points on this line lie in the orange region like this. Some points here lie in the orange region, but some points lie in the green region. On the other hand, for this function, every point on this line lies in the orange region. So this is called a convex function and this is called a non-convex function. There are more mathematical definitions for convex and non-convex functions, but I'm giving you a graphical interpretation of what a convex function is and what a non-convex function is. I'll tell you why. Convex functions have only one minima or one maxima. Like for example, take this. There is only one minima, right? And there is no maxima for this. Okay. On the other hand, I can draw one more function like this, which looks like this. This function has one maxima here. It doesn't have local minima because it can keep decreasing. On the other hand, if you have a non-convex function, in other words, before we go to non-convex functions, for convex functions, your local minima is equal to your global minima. Because there is only one minima, right? Or one maxima, right? So your local minima is equal to your global minima. For non-convex functions like this, you can have multiple local minima, right? Of course, there's only one global minima, but you could have multiple local minima. There is always only one global minima anyway, right? So that's a fundamental difference between convex functions and non-convex functions. A very, very important thing. A very, very important thing for you is your logistic regression and linear regression, even SVMs that we have seen, all of them, in all these cases, the loss function we have that we are optimizing for can be shown to be a convex function. Which means if you find local minima for logistic regression, linear regression, SVM, all sorts of SVM, linear SVM, nonlinear SVM, RBF SVM, all of them, you can prove mathematically that your loss function is convex, and hence for all of them your local minima is same as your global minima. So once you find a minima, you're done with this. The important part is for deep learning algorithms, like your multi-layer perceptrons, right? They are shown to be non-convex loss functions. The loss function that you have in the case of deep learning, except in the limiting case of logistic regression. Logistic regression is also a special case of deep learning, right? Which is actually not deep, which is literally one neuron with a sigmoid activation, right? This is convex. But if you have if you have maybe two layers, if you have two-layer neural network, not just a single neuron, but even a two-layer neural network, the loss that you get, the loss function that you get is a non-convex loss function, which means you can have local minima, you can have saddle points, right? And you can have multiple local minima, right? And once you have a local minima, you can get stuck at a local minima also, right? So let's look at this. Suppose I'm trying to solve my logistic deep learning problem, and this is my W. And let's assume my loss function looks like this. Okay, suppose I started here. Okay, let me just change the color here. Suppose this is my initial W. This is my W0. Okay, so I'm doing gradient descent. I come here, I come here, I come here, then I get stuck because the gradient here has become 0. So if this is my W in the 0th iteration, this is my W in the first iteration, W in the second iteration, my W in the third iteration, if it is here, I'm stuck here. And what I got here is a local minima. What I got here is a local minima, while the global minima is somewhere here, which I can never reach because I can never come out of this, bottom. I can't climb up. Okay, so there is a hill climbing analogy that you can think of. Optimization is about trying to climb or descend a hill. Suppose you're here, and it depends on the initialization. Suppose if I start here, suppose if I started here, let's say if I started here. Okay, suppose this is my W0, let's say. I keep coming down and I'll reach here and I'll get stuck here because here the gradient has become 0 and my W new will be equal to W old because this gradient has become 0. When this gradient becomes 0, I cannot move any further. And if I started here, if this is my W0, this becomes my minimum. So in deep learning, what happens here is because it's a non-convex loss function, there are multiple local minima, and based on where you initialize, based on your initial value of your weights, you could land up at different minima. You could land up at different minima, right? So what we have seen here is a 2D case, right? See, all these functions I've seen are 2D cases, right? I'll also show you a hill descent. So this is like hill descent, right? Because you're here, you're trying to climb down a hill if you want to find a minimum, right? Similarly, if you're here, even if you're here, you're trying to climb down a hill, come down a hill, right? The most important concept here is about convexity and non-convexity, about having multiple local minima and global minima, and the fact that deep learning, multi-layer deep learning, is a non-convex function means that depending on where you initialize, depending on whether you initialize here, whether you initialize here or here, you could get different minima that you can end up at.